Have you ever wondered what happened to the world's largest marine predator? Sometime between 5.33 and 2.58 million years ago, during the Pliocene epoch, the Earth went through some significant changes over a relatively short period of time. The occurrence of important geological events like the configuration of continents, development of ice caps, and global cooling led to an Earth very similar to the one we know today. Marine life flourished with a huge amount of diversity following the Cenozoic adaptive radiation. If you were to go swimming in the Pliocene seas, you might encounter the recent ancestors of modern whales, pinnipeds such as seals and walruses, and many species of cartilaginous fish. Among the fish with cartilage-based skeletons was the Megalodon, an apex predator and dominator of Pliocene marine ecosystems. In the recent study, Endothermic Physiology of Extinct Megatoothed Sharks by Michael Griffiths et al., the trophic status of the Megalodon and its relatives were confirmed. The study used analysis of bioapatite, a substance that's particularly abundant in bones and teeth of animals, and it's conserved in the fossil record. Bioapatite is a crystal structure composed primarily of calcium as well as phosphate and hydroxyl groups. In this crystal structure, there are also trace ions such as carbonate, zinc, and fluoride. The trophic level of an organism is deduced by studying the zinc isotopes within its enamel. Data for body temperature, on the other hand, is found by analysis of the oxygen isotopes in bioapatite's phosphate groups and carbon isotopes in its associated carbonate groups. The results of spectral analysis of the Megalodon's bioapatite correlated with a very high trophic level and an elevated body temperature compared to its surroundings. Figure 1, one of the graphs from Dr. Griffith's study, shows shark teeth from the Miocene and Pliocene epochs as triangles and circles respectively. It also demonstrates the differences in thermal physiology between the Megalodon in red, ectothermic sharks in blue, endothermic sharks in yellow and orange, and endothermic marine mammals in dark red. This graph reveals that Megalodons had elevated body temperatures compared to other ectothermic and endothermic sharks. The Megalodon's success and its heightened body temperature is actually linked. When an organism is able to regulate its own body heat, we say that it exhibits endothermy. Isotopic analysis of the two fossils left by Dr. Griffiths shows that the body heat for Megalodons was on average 7 degrees higher than the theoretical sea temperature. This means that unlike modern sharks, who are mostly ectothermic and rely on ambient temperature, the Megalodon was endothermic. Endothermy contributes to the average cruising speed of aquatic organisms as well. An organism that is able to regulate its heat is an organism that is conserving energy produced in its muscle cells. This means that the Megalodon can maintain a metabolically favorable temperature, a temperature that is the most ideal for energy-producing processes. This allows muscles to work harder in exchange for an incurred metabolic cost, giving the organism superior speed and durability. The Megalodon's ability to regulate its body heat is what allowed it to dominate in its niche, but it also led to its downfall. Figure 2, the graph from the study Zinc Isotope Ratios of Bones and Teeth as New Dietary Indicators by Clairvia-Jouen et al. Shows a trend of zinc concentration as you move up in trophic level. Zinc 66 is accumulated in primary consumers, and its concentration diminishes significantly as you get into the secondary and tertiary trophic levels. Figure 3, the scatter plot from Endothermy Makes Fishes Faster by Lucy Harding et al. Shows a strong positive correlation between endotherms of higher mass and higher speed. Data shows our Megalodon was clearly an endotherm at the apex of the trophic pyramid with very high cruising speeds. Around 3.6 million years ago, cooling seas during the Pliocene epoch led to bottom-up trophic changes, which resulted in the extinction of the Megalodon. As temperatures fall, zooplankton and phytoplankton became far less prolific. This diminishes the population of primary and secondary consumers, meaning there is far less prey available for the Megalodon. Low sea temperatures also mean a higher metabolic cost to maintain an ideal body temperature, so each Megalodon would have to consume a lot more prey to survive. According to Dr. Griffith's study, the combination of higher metabolic cost and prey scarcity likely led to the extinction of the Megalodon. As the climate changed, the Megalodon's greatest strength became its greatest weakness. Following the extinction of the Megalodon, a top-down trophic disruption occurred. Great white sharks, which competed with the Megalodon for prey and territory, were able to rapidly grow in population size. The loss of a significant predator also meant that the populations of the lower trophic levels grew, as organisms that would have been the Megalodon's prey survived. These two trophic cascades show how the disruption of just one niche can have far-reaching ecological impacts. The decreasing ocean temperatures didn't just affect the organisms who depended on warm oceans, it affected every single organism in the local marine food web. We can apply this knowledge to modern conservation tactics. The Megalodon is an example of how one small disruption can totally upheave an ecosystem status quo. There are a few limitations to Dr. Griffith's study, though. One limitation of this study was the limited amount of data that could be analyzed. Here, teeth of the Megalodon were the main subject tested, which would only give a minimum estimate of the Megalodon's body temperature from the Delta-47 isotope. Because of the peripheral location of the teeth and the sheer volume of the Megalodon, it's hard to make concrete statements about the entire body temperature from the conditions of the teeth alone. Thank you so much for listening. We hope you enjoyed our presentation and learned a little bit about the disappearance of one of the most celebrated marine predators in history.